Hello and welcome back to a new video in my real-time rendering video series. Now, this is the first video where we actually gonna get started and talk a bit about what we are doing. Again, this is just gonna be a lightweight video today, so we're just gonna get started. And well, today's topic is, what does it take? Well, the idea is that you're gonna be aware of what the scope of this task is that we are doing, right? Last video we talked about what is real-time rendering, what this video series is, what this video series is not, and what we're gonna do today is I'm gonna bring you some awareness on what it actually means to do real-time rendering. Alright, so before we're gonna get started, let's maybe talk a bit about how this video is structured. So, what does it take? It's the title of the video today, and this is the content of what we want to do. Well, first of all, we're gonna again take a look on what we want to achieve. We want to take a look at what are the requirements, what is the thing we're gonna start with, and what's the thing that we're gonna end with, right? That's the idea. We're gonna get to that. Then after that, we're gonna go to a very important slide here in this presentation. What does that mean? That's the most important thing that you need to get into your head. What does it actually mean to do real-time rendering? In numbers, right? This is gonna be mathematical. And I'm also gonna have a bit of an example for you there, but what does it actually mean? And you're gonna see that we can fail totally on doing that a naive way. Well, after that, we're going to talk a bit about how we then going to achieve that. Because, well, the brute force way is not going to work. I'm going to already spoiler that. That's not going to work. And we then need to talk a bit about how we achieve that. And after that, we're also going to talk about how we realize that. So, achieve is more like a broad way. What are we going to do to achieve that? And then we're going to talk a bit about how we are realizing that in terms of video, code, structure, and so on. You're gonna see. So let's get started by asking us a question. What do we want to achieve? Well, we already talked about this last video. We want to render an image. An image on the screen, a nice little image like that. We want to render geometry, colors, and have this all move around and look beautiful, right? That's just an example here. Open world game Mirror's Edge Catalyst, and you can see like that we have like all these buildings here. We have the billboard that is yellow. We have some orange highlight on that building there. Some blue highlight on that building in the back there. Some UI elements drawn in here. Yeah, is it UI? Kind of UI elements drawn on here. We have all this building, and yeah, we have a nice scene how the devs intended it of the game. Right? That's what we want to achieve. And actually, if we would just want to achieve an image, easy. Model it in Blender, click render, wait a few days, finished. But what we do in real-time rendering, and that's a big thing that's making this a hell of a lot of more complicated, we want to do this at least 16 times per second. 60 Hz is the rate that we need to have at a minimum. It's a golden number, 60 Hz. Earlier on especially on console platforms, it was 30 Hz, especially because televisions weren't that fast to display all these images, but every computer monitor that you're going to buy is at least going to have 60 FPS or 60 Hz or 60 frames per second, refresh rate, 16 milliseconds, I think, if I'm not mistaken. What it is doing. So 16 times a second, your monitor is at least going to show you the image, and that's the requirement for ourselves. I mean, most people would now yell at me and say 60 Hz is not enough, and yeah, especially if you're doing competitive games like competitive shooters, 60 Hz is actually not even enough. You're gonna go for something like at least 120 Hz or even more. But in our case, we want to do beautiful physical-based rendering with rich scenes. And yeah, our focus is not gonna be on competitive shooters. Our focus is gonna be on single-player, open-world story games. Right? That's like the thing that how I want to see this. On what I would, or at least this is like the game that I would do. Single player, open world game. That's what I would do if I would have a renderer and a whole shed full of artists that produce art for me. Lol, because I don't have them. Artists are my biggest problem. If I wouldn't have artists, if I would have an infinite amount of artists working for me, I would be up on an existing game engine doing games and not teaching programming videos. But yeah, that's the issue here. All right. So yeah, what do we want to do, right? That image here, 16 times per second on a, now you're going to get numbers, 4K monitor, 3840 times 2160 pixels. This is our goal, right? Full screen image, 4K, 60 hertz a second. If we don't hit this, I need to fix it. We need to fix it. Maybe because I might change with something on my background systems that might optimize stuff. But in general, we need to fix that to make that condition work. However, that condition is not something that comes out of nowhere, right? If you have just a full screen image, right, I can write this to you. I can use tricks to always generate these. I could use the slowest programming language in the world. Maybe we could do this in Excel as well and use each cell as a pixel, right? I could write here some VBA macros that fill each Excel cell with a black value and done. Because if we just have an image, it never changes. If we need some input, if it doesn't change, we can just take a long time to compute it and then show the same image every 1 divided by 60. I think 60 milliseconds is it then? I'm not quite sure. But that's not the point, right? A full screen image needs to have some source. And in this case, I already talked about that in the scene. We have some geometry data, we have some color information, some position where everything is located. Additionally, we have some player input where the player is currently located, how he is moving the mouse, or she, or it moving the mouse, and as well, the actual engine driving all that stuff. If the engine is moving objects, it needs to be reflected as well, right? So we have all that input data, that data above here, that input data that we have, and what we need to do is, like the developers of the renderer, we need to do processing. We're gonna get a massive amount of input data per second, not per second. When the level loads, we need to evaluate these per frame. With some additional data that we get on a per frame basis, we need to do some processing on that. Spoiler alert, CPU and GPU, even though we're going to get to that in more detail. And when all this processing is done, we can poop out a full screen image to the screen. That's the point, right? Very simple task. Well, might be. Well, just 3 little boxes and we just deal with one? Yeah. If it would be that simple, we would have more game engine than people on Earth. No, I don't think so. But in general, you get the point, right? It seems simple. Just to do a bit of processing, right? Just some I equals x plus y times 5. No, it's not as simple as that. We actually need to take a look at the numbers. What does that actually mean? Producing a 4K full screen image 60 times per second. What does that mean? Well, let's do the math here. Okay, so what we're definitely going to do is pixel processing, right? If we're going to output 3840 by 2160 pixels 60 times a second, we also need to process them, right? Because every pixel can change. It might not change, but it can change. And we need to always take a look at the various condition. If we maybe have a level change, the user's in the loading screen and we get the level, every pixel changes. So we need to be able to do this every frame, to change and draw every pixel on a per frame base. And what I care about is the bitrate. We want to go to something called a bitrate. The bitrate is the number of bits per second that we need to throughput through our systems, and it's always quite a nice measurement so that we know what's actually going on and what the scope is of what we are doing. And to get to that, we need to do a bit of math, right? First of all, how many pixels do we have in a frame? So 60 times per second, we need to present an image, and this image is called frame, and we need to be aware of how many pixels we have in a frame, right? This math is quite simple. We have 3840 times 2160 pixels, so just multiply these numbers together, and you're gonna get the number of pixels per frame. 8.3 million. Yeah, 8.3 million seems reasonable. But already a high number, right? Because like 8 million datasets, you're gonna get something like that on any certain task that you have done in the future? I think not. I think this is the biggest task that you're gonna do ever, outputting a 4K image, right? Probably if you have done some data acquisition once, maybe you have worked with datasets larger than 8 million entries, but I don't think so. So 8.3 million is already a quite significant number. However, this is not the end, because this is just one frame. However, our condition here is to have at least, so a minimum requirement of 60 of these frames per second. So what you need to do is you need to multiply 60 in there as well. So multiply 60 with the 8.3 million that we already got. It's going to lead us to something below like 500 million pixels per second. 500 million. That's a big number, right? 500 million. Just see this. If you convert each pixel to money, you're going to be rich. Already, if you just take your normal monitor, just one frame, if you could convert one frame to money, you are rich. Just imagine that, right? Take a look at your monitor and see, oh, if I could convert every pixel to $1 or €1, I'm going to be rich, right? And if I'm doing this 16 times per second, I have more money than I can ever spend, right? Okay, but just that you kind of like get the point on what's happening there. However, this is not even where we're going to go to, because like a pixel it's a virtual unit, right? It's not the minimal unit that a computer can do. The minimal unit a computer can do, the minimal unit of signal that we can send through a cable, it's a bit, right? 0 or 1. Asterisks, we as electrical engineers do know tricks how to send more over cables and have done quite some research to make this faster. But in general, you normally, if you keep things simple, per clock cycle you can transfer 1 bit. And that's where we want to go to. But a pixel is not a bit, right? A bit is just a 0 or 1. It's just a binary state, 0 or 1. However, we're going to talk about pixels. How is a pixel composed? You should know that. It's composed out of 3 color values, RGB. Most of the time, they are 8-bit of a size. If you have an HDR monitor, there might be more bits per color. And you need 3 of them. RGB, red, green, and blue. 3 times 8 bits is that. 3 times 8 multiplied by the 500 million that we already have pixels, and you're gonna be ending up with that big number, 12 million, billion? Yeah, billion, I think. 12 billion bits per second. 12 billion. Take a look at this number, how many zeros it has. Like 12, 0, 0, 0, 0, 0, 0, 0, 0, 0. And you get it, it's a bit less, like 50 millions. We can throw them under the table. We don't need them. However, like average of 12 bits per second. 12, not bits, sorry. Billion bits per second, which is converted to a bit more reasonable number. 12 gigabits per second. It's a large number, right? If you are taking a look at your computer is connected wired to the internet, not to the internet, but to your ISP's router. So if your computer is connected via cable, the chances are going to be really, really high that this cable can transmit 1 gigabit per second. Just 1. So just imagine 12 Ethernet connections between your computer and your monitor. This is what it takes to meet our minimum requirements. 12 Ethernet cables from your PC to your computer. That's massive. Of course, there is also network equipment that can do more, like 100 gigabit fiber optics and stuff like that, but that's advanced rocket science and hard, expensive hardware. But still, like on a normal home network, gigabit is currently the thing, right? Even though you might be on 2.5, but normally you're just on a gigabit currently. 12 of these gigabit Ethernet cables just for the transmission of the image, of the pixel processing that you're doing. And actually, that's actually not the end, right? The pixel processing is not where it ends, because the pixel processing is our output. It's our last stage. The last stage is that every pixel needs to be computed. However, we are not near our input data. We first need to do even more stuff. We need to take a look at a massive amount of objects, like something called geometry processing. Open world games, we have millions of meshes of geometry that needs to be rendered. We need to take all of this geometry into consideration. Take a look at, okay, what geometry shall we render? What is in the current view of the player? What is not? What can we discard? What do we need to render? And if it needs to be rendered, we need to actually make sure that it's rendered at the correct position. We need to make sure that it is converted from a 3-dimensional representation of geometry into a 2-dimensional plane, the actual image. Then we need to take a look at, if it is projected into this 2-dimensional plane, which pixels are actually covered by that geometry, covered enough that we're going to do this. Then we need to evaluate each color value of these pixels. These color value evaluations, they require lookups in one or even more textures. And if you have, textures are images basically that contain color information. And if you have done all those lookups, these needs to be processed together. And these process process to gather data needs then maybe another more processing with the condition of lighting, if it is in shadow or if a light is directly shining on it, and then you are done with one pixel. So additionally to all the pixel processing overhead, we get like again, another more geometry processing overhead, millions of measures that need to be evaluated if they shall be rendered. Of course, I know that there are techniques to make this fast and quite fast, and not a hard task actually, but right, just to get the scope of what we are doing here, and this is massive. The theoretical brute force throughput of an application that is growing exponential with each like object that you're gonna add to it. Maybe not exponential, but because at the end it's gonna be linear, but you just get the point, right? Everything that you're gonna add, as bigger your game's gonna get, as bigger your scenes is gonna get, as more complicated your stuff is gonna get, the complexity is rising. It's rising. It's nowhere controllable, and that's our job, to make all of this controllable. Not, of course, only our job. There are a hell of a lot of more people involved. People that design graphic cards, people that design CPUs, people that do research at universities at their work, like for example EA, a big company like EA or Ubisoft. They have like an own division of people that are just dedicated on trying to solve problems that make this feasible. And just to show you what's happening here, I've prepared you something, right? This is a normal Windows command prompt. And what I want to do today now is I want to write a brute force Python program that tries to compute a value per pixel. So remember, we are not doing geometry processing now. We are just going to simulate pixel processing, okay? And we're going to try this out with a 4K image with that bitrate that I have done. So let's do this. We're going to define a Python function. We're going to call this pixel_proc for pixel processing. And we're just going to write some code in that function, right? What we do want to do? Well, we need to process each pixel. So for P in range of how many pixels do we have? 11, 9, 4, 3, 9, 3, 6, 0, 0, 0. That's the range of pixels that we need to compute. And what do we want to do on a per pixel base? Well, this is now hard because what is the scope of pixel processing? We don't know that, but it's going to be quite complicated what we're going to end up with. But I'm just going to do a nice simple value. So let's do something like color equals something like, let's maybe first define some components. We have like a red component, which has a value of 10. We have a green component with a value of 200, and a blue component with a value of, let's say, 55. And then we have some alpha components, some transparency that we want to apply. Let's say the transparency is 128. And what I want to do is I just want to combine this into a grayscale. I'm now doing a very horrible grayscale conversion. This grayscale conversion is something that you would definitely want to do better. And yeah, let's just do some simple stuff. Let's do some simple stuff and do something like R multiplied by A plus, or let's do it differently, R multiplied by A plus B multiplied by A plus G multiplied by A. Now we've done this in the wrong order, but it doesn't matter. And divided by 3 to normalize it, right? Just a simple equation like that. Okay, so we are done with that function. Now let's call this function pixel_proc. And what I'm now expecting, since this is our bitrate, I'm expecting that this runs exactly 1 second so that our throughput is satisfied. So I pressed enter, and I'm now already talking longer than it should have taken. And I'm going to tell you something. We can wait a significant amount of time, and it's not going to return. I haven't measured how long it takes, but I have waited 10 minutes, and then I was sitting there and said, no, I'm not gonna wait. Maybe it's gonna complete if the video is finished. I don't think so. Well, we could have tried this Python command that tries to time stuff, but I'm not a Python expert, so I can't tell you how I can time stuff in Python. I just know Python for what I use it. And yeah, you can see it's not gonna complete near our requirements. So brute force way in Python, doesn't work. Brute force way in C++ would be faster, especially if the compiler sees that we are not doing anything with these values and discards them, then it's instant. However, if the compiler does not throw out code and is not smart, in C++, it's going to be faster, but also not near our requirements. And actually, on geometry processing, I would say, all right, we can optimize this. On pixel processing, At the end, every pixel needs to be computed per frame. So this is the minimum bandwidth that we actually need to be able to satisfy. And it's not going to do this. Not in Python, not in C++. It's only gonna work on GPUs, and GPUs have special hardware, electronics that are built for just handling tasks like that. There's also some math that's gonna be executed on a per pixel base, which is highly parallelized on a GPU, but again, this is something we're gonna talk about in the future videos. Just a bit on board you of the scope of what we are doing, right? So you see the problem, what we need to optimize. And this is only going to get worse. This is not feasible to do on a CPU in Python and C++. And that's what we are solving. We as rendering engineers, rendering software engineers, we try to make this fast with any tricks that we have. And not only fast, it also needs to look good. Right? That's what I've done. It's just going to output a constant color per pixel, and that's not good. So it also should look good, be customizable, be changeable on a runtime, 60 times per second, and all that stuff. It's going to be insane. So how do we going to achieve this? Well, we're going to achieve this by writing components. We're going to write 2 components in our tutorial series. We are going to write tools, and we're going to write a renderer. These tools are going to be responsible of doing some geometry preprocessing, maybe compressing images and textures, computing stuff, and outputting binary files that can be used fast. Because, well, geometry comes in like FBX formats or OBJ formats quite commonly, and we can't use them. At least not in shipping, because they are slow to load, they are proprietary and large, require providing large libraries to be loaded, and it's just a total carnage. So what we're going to do is we're going to write a tool that does all that pre-processing for us and outputs file that we can natively read and maybe even directly natively upload to the GPU, but that's topics that we're going to talk about in the future. And what we then later do after all of our tools are finished, we're going to write a renderer, and the renderer is going to process geometry. It's going to check what to render, take a look at all the geometry, evaluate what do I need to render currently, then go on, render it. We need to process lights. That's also something that we're going to talk about. Lights that are going to be placed in our scene so that we know how the lighting is, because physics-based rendering, let there be light. Without light, there is nothing to see. And we also need to process all these lights and make sure that they are rendered correctly. At a certain point, if you can say rendered on a light, bit hard term, but yeah. Rendering the pixels, of course, based on cameras, geometries, and light, be able to render them correctly, and then after it layering effects on top of that, like motion blur. What also effects could you see? Bloom effects, that say something to do, screen space ambient occlusion, screen space reflections, maybe ray traced reflections, ray traced ambient occlusion, ray traced shadows, non-ray traced shadows. There are so many effects that are faking good-looking images that we're gonna explore. I'm not quite sure how I'm gonna tackle this. That's something I'm gonna decide if we're gonna do the classical methods first and then try to replace them with ray tracing. Maybe. Let's see. Let's see where the series is gonna lead us. So yeah. Well, how are we gonna do that? Because, as you can see, this is not feasible. Well, of course, we're going to do this with math. We're going to realize that with math. And this is a equation. This is the rendering equation. And this rendering equation, which is visualized by that image, I'm not going to go into the details what it does. If you can find a way to exactly compute this equation 60 times per second, and you're going to try to sell this, people are gonna pay you millions. And not only the gaming industry. If you can solve that in real time, you're gonna get a lot of money. Because this is the rendering equation. If you can exactly compute this rendering equation, the computer images that are displayed on the screen are gonna look the same than a photo. if you have the same input data, of course. But again, if you can solve that with a large set of input, of course, this asterisk, of course, for simple scenes, you can solve that. But for like real-time looking scenes, like take a scene from like Tomb Raider, Mirror's Edge, or any like good-looking game, and double the features and the resolution of all assets times 10, and you can still exactly compute this equation, you're gonna be the god of rendering. Because this equation is not solvable, at least currently not, for complex scenes. So that's the math, we're gonna get to that, what it is, if we are getting to the theory of what's behind that between Lightning and the Lightning model, which is what this is all about. But for now, just to scare you away from the theory is some advanced math. And how are we gonna realize this? With a PBR. A physical-based renderer that we're gonna write. So a renderer that's gonna get some geometry, uses some math, gets some images, gets a current state, uses some more math and light information. It's not in a certain order how I've told that, by the way. And yeah, so many informations flowing into a renderer, producing an image. That's how we do it. Already talked about that. The renderer, our glory feature that we're going to implement in this series. And believe me, I have at least like 10 times work additionally to do to write all the other systems so that we can do this. Okay, maybe not 10 times, but 3 to 5 times to get all the context right, to just bring you compressed coding videos. And that's why I think that coding videos in this series are quite far away. Right then. I think that's actually it, is it? Yes, it is. There we are, end of the video. So, by the way, Python has not finished yet. A C++ application might have finished. I'm kind of tempted. Okay, since we're at the end of the video, let's see if we can write in time a function in C that is going to beat the Python, right? No Visual Studio today, just a Notepad, because you can use a Notepad to write code. Alright, hashtag include. Now do I need IOStream? CSTD int. I need CSTD int. Int main. And what I want to do is I want to write a for loop. Is it a tab actually? It is. Odd. What is that for a tab size? I don't care. C++ doesn't care about tab sizes, so I don't care as well. So for uint64tp equals 0, p smaller 1194393600 plus p. So uint 8t, this is how a pixel looks, r G, what is B? 55 and A equals 128, so we're gonna have all these values. Alright, so what can go wrong when you are a C++ developer and you try to write something with the editor and the Visual Studio developer command prompt? Well, you end up with x68 and you consume more than 4 GB of memory and you think your application is fast, but it hasn't run at all, and yeah, bad things happen. Right, we need a 64-bit environment, which I have totally not done. Let's comment in my measurements. Now, you haven't seen how I have written that code, but it is in general the same code. I've just added some debug outputs that I can quickly remove just to walk you through very quickly. I'm actually doing more than in Python because I'm actually storing these values. I'm assigning or allocating like 11 GB of memory, and I can do that. You might not be able to do that. I'm allocating like 11 GB of memory. I'm just allocating some array here, getting my high resolution clock now. I'm doing a for loop over all of these, and I'm just doing a bit of math here, similar to what I've done in here. Then I'm ending that, elapsing it, and printing out stuff, right? So let's see D2C, and now I should be able to do like a CL dummy.cpp, which should give us some errors because it wants us to compile this with ehsc, so do it if you like. And then we can run this by calling dummy.exe, and we're gonna see in a few seconds what our result is gonna be. How long is it gonna take? Alright, so here we are, like approximately a minute. It did run like 61,000 milliseconds. So yeah, approximately a minute. It's required to run a minute, and Python is still rolling. It also required quite a lot of memory. This should be also, I don't know if Task Manager, do you have historic values on memory? No, you don't. But if I would run dummy.exe, you should see a peak here. Why don't I see a peak? Where is my peak? What the actual hell? Why do I not? I mean, I see it because Microsoft is consuming it. Okay, it seems like Microsoft is a bit smarter than my application, and it's swapping or it's page faulting and bringing in the memory. This is why it's growing linearly and it's not growing exponential because, well, Microsoft is waiting until it gets page faults until it actually gives me the memory that I requested, because it says like, well, the application wants like what? 11 gigabytes of memory? Is it approximately? Well, the application wants 11 gigabytes of memory. I don't think that this is correct. I'm not going to allocate them straight away. I'm going to wait until the application accesses it. I'm going to get a page fault, and then I'm going to allocate the memory. So that's why this is now not giving me a peak. It's like slowly going up, but it's like operating system safety. If you have a faulty application, yeah, it would do this differently. Now, of course, freeing is a peak, right? It's a peak down, but it's growing. I don't want to go into how operating systems work. I actually did once consider writing an operating system with a YouTube series, but that's not happening. Real-time rendering is what's happening now. Maybe this is going to happen in the future. If I can do YouTube full-time, I could dedicate myself to something like that. Asterisks. But yeah, consuming much memory, being fast, and Python. Not gonna happen, I think. Definitely not gonna happen in this video. So I'm sorry. Sorry, Python, 30 minutes wasted versus a minute in C++. And now divide this actually, because this is actually not what we should get in a second, because it's a bitrate, and I don't know. But having the bitrate as a throughput definitely guarantees us that everything works. And C++ is promising, right? It's just a factor of 60 that we need to compensate. 60 times faster, while Python is like infinite faster. Would be quite interesting where Python is, but I can tell you. But no, that's enough for today. Thank you for watching. Have fun learning. Videos, again, will come when they are ready. This is not a regular video series, even though this video is kind of regular now today. But yeah, I hope I can keep it up. This is just a disclaimer, right? Especially later on. So, hope you had fun. Please make sure to like and subscribe the video. Yeah, to like the video and subscribe to the channel. That really helps. Really, that meant something, because as I already told you that, the more support I'm going to get, the more time I can dedicate into the channel. So yeah, I don't want to be too much begging, but thank you for watching. Like and subscribe. See you in the next video, and have a nice day. Bye.